Okay, so we're going to go through our third and final set of notes over bonding. Start by making yourself a Frayer model. I put some review instructions in Canvas there for you. Once you have that made, we're going to move on. Our topic for today is metallic bonding. So it's the third and final type of bonding we haven't discussed yet. As much as ionic and covalent seem like opposites, we're going to find out metallic bonding is very, very different from those other two. So we really have three very different kinds of bonding going on. So put metallic bonding in the diamond in the center, and we're going to have the same quadrants we had before. Okay, so composition of the bond, what makes up a metallic bond? So put that as the title of the quadrant you choose. And what makes up a metallic bond is metals, okay? It is based on what metals are involved in the bond there. So we're going to see that metals tend to have highly mobile valence electrons. So like this would be worth writing down. Metals have highly mobile valence electrons. We even sometimes call it a sea of electrons. As I mentioned in a previous reading, like a school of jellyfish just float around in the ocean and you can't say what part of the ocean belongs to which jellyfish. Really the same thing going on here. These electrons are free to move all around. We call them delocalized. That's a vocabulary word you might want to write down. So metals have the highly mobile valence electrons or sea of electrons. We can also call that delocalized. Okay, so that's three ways of saying the same thing, but I would recommend you have all three there on your paper. Okay, quadrant two, the elements involved. Well, I'm sure this is a shocker, right? Okay, so metallic bonds form between metals. There we go. We need it between elements that have a small difference in electronegativity. And so that again means elements close to each other on the periodic table. But if you kind of look at the periodic table, you can notice that we have a lot of metals listed on the periodic table. So there is a large, a wide difference in the characteristics of metallic bonding because it depends entirely on which metals in particular are being put together, okay? So you want to write down it's between metals and just know that it really, really depends. The characteristics is going to depend on what metals are involved there, okay? How strong is metallic bonding? So third quadrant, strength of the bonds. Metallic bonding, again, depends on the metals involved. So how would I know if these two metals are going to be stronger or weaker than these two metals? Okay, so we would measure that. You do want to write this down, okay? We would measure that with a heat of vaporization. That's the heat energy it would take to vaporize, to boil into a gas, a vapor, this metal. Now you can imagine that's actually a big number because, think about taking a metal. First, you'd have to melt it, and then you'd have to heat it up more to boil it. But that's how we measure this. It is the heat of vaporization. So let me go back a few notes. Ionic bonding, it was lattice energy. Covalent bonding, it was bond energy. With metallic bonding, it's heat of vaporization. So notice it's a different way of measuring the strength of the bond every single time. So you need to know which vocabulary word goes with which type of bonding. Be careful about that, okay? So have down heat of vaporization, and if you want the definition, which would be a good idea, it is the energy required to make the metal a gas. Okay. Fourth quadrant, properties of the compound. Now, these are going to be very, very different than we've had before. Because again, as much as you would think ionic and covalent are opposites, and we've covered both ends, there really is this third weird category of metallic bonding going on, okay? Because of the sea of electrons model, because these electrons are not strongly held by any of the atoms involved, that gives metals very unique properties. Check this out, how this is different. They're good conductors as a solid. No other kind of bonding had that. Ionic bonding did not conduct as a solid. Covalent bonding did not conduct ever. And here metals, yeah, they should conduct as a solid. That's wire, right? Okay. Malleable. This means when you hit it hard enough, depending on the metal, you're going to bend it. It's not going to shatter. So that's a contrast to the other two. Ionic and covalent, if you hit it hard enough, they will shatter into little pieces. Metals will bend. They're malleable. The word comes from the word for mallet. All right. So hit it with the mallet, and what's going to happen? You're going to bend it, shape it, smash it thinner, but you're not going to break it. Ductile means to be stretched into wire. Would you think about taking a sugar crystal and like trying to pull it long and skinny? Can't do that. It's going to break. What about some salt? Take some salt crystals and stretch. Oh, it's going to break again. But take a little bit of metal and try to stretch it, and you actually could. We use metals for wires because of this. The word for that is ductile. It is going to hold together as we stretch into wire. We're going to see metals tend to have very high tensile strengths. That is, they resist breaking when pulled, which goes into, again, it's almost saying the same thing as they're ductile and malleable. They all come from this sea of electrons as the root cause. Because of the sea of electrons, they resist breaking when pulled. They can be pulled into wire because they resist breaking when pulled. And if you do hit them hard enough, you're going to bend them, not break them, because they resist breaking when pulled. Okay. Fancy word you probably want down, and maybe need to rewrite the definition too. Lustrous. They have luster. Now, way back when you were probably in kindergarten, one of the first things that you were probably talking about when you talked about metals is you thought metals were shiny. Yeah. Well, we're used to that. Metals look shiny most of the time, right? That is luster. And the reason they look shiny is because of the sea of electrons. So again, all these characteristics come from the sea of electrons idea. No one atom of any of these atoms really hold on to the electrons at all. And then metals, probably not a shocker. Metals don't dissolve in water. Again, water dissolves polar and ionic things, and metals don't have ions. They don't have poles, and they don't have ions. So water will not dissolve metals. They'll sink or float or something rather, but they won't be dissolved. All right. So if you still need to write some of those down, pause the video, write it down, and then unpause as we go. Okay. I want to talk to you about I had a video that was supposed to play. I'm supposed to play. Here we go. Okay. I wanted to show you a picture of what the sea of electrons model really does and how it compares. So great, amazing video clip about to show you that shows you all these characteristics of metals I just talked about. So be certain you pay attention, because this is a great visual to go with all those characteristics.
Metals are shiny, malleable, ductile, and good conductors of heat and electricity. The structure of metals and the nature of metallic bonds explains some of these typical features. Metals are made up of positive ions closely packed together in crystalline solids. The positive ions are surrounded by a mobile sea of electrons. These valence electrons are free to move away from their atoms of origin. When one electron flows away, another one moves in to take its place, due to the electrostatic attraction between the cations and the electrons. This is the nature of metallic bonding, what holds a metal together. Compare this image of a collection of cations surrounded by a mobile sea of electrons with ionic bonds, where oppositely charged ions are held together by electrostatic attraction, or covalent bonds, where two uncharged atoms share their valence electrons. Metallic bonds are much weaker than either ionic or covalent bonds. The highly mobile sea of electrons is responsible for the shininess of metals. Photons of light are more readily absorbed by free electrons, which can easily jump to a higher energy level. Then, when they fall back down a level, the energy is re-emitted as light. The color of the metal is determined by the wavelength of light which is re-emitted. Similarly, this free flow of electrons explains the ability of metals to conduct heat and electricity. When you heat up a metal, the free electrons quickly start vibrating. Increased kinetic energy means increased temperature. When an electric current is applied to a metal, electrons enter from one side, causing repulsion and generating movement within the sea of electrons, and an equal number of electrons exit the metal as the number that entered. The mobile sea of electrons also explains the malleable nature of metals. If you strike an ionic crystal with a hammer, it shatters. This is because the applied force pushes like ions close together. They violently repel each other, breaking the crystal apart. In contrast, if you hit a metal with a hammer, it doesn't break, it just dents. Metals are able to deform in response to an applied force. The mobile sea of electrons shields the cations from each other, preventing violent repulsion and allowing the metal to change shape. The most malleable metal is gold. A similar property to the malleability of metals is their ability to be pulled into long, thin wires. We call this ductility. Ionic compounds are not ductile for the same reason they are not malleable in general. If an ionic compound is forced into a long cylinder, it breaks apart because of the repulsion of like ions. In contrast, a metal can be pulled into a long cylindrical shape because the cations can line up, shielded from each other as the fluid-like sea of electrons flows around them. The most ductile metal is platinum. Almost all metals are solid at room temperature, the cations forming a recognizable, tightly packed shape. Can you think of the exception? Mercury is the only metal that is liquid at room temperature. There are 4 other metals that melt very close to room temperature: francium, cesium, gallium, and rubidium.
Okay, so that was a great review of the characteristics of metals and how it contrasts with our other types of bonding. So I hope you have that mental picture now of how unique metallic bonding is and how all the properties for metallic bonding come out of that. Okay, we're going to move on to our special topics on the back of your Frayer model. All right. Our special topic when we talk about metallic bonding is on the topic of alloys. So first off, a definition. Alloys are a mixture of metals, or sometimes we do use some nonmetals. The goal of an alloy is to get new properties by mixing them. Now, this is a physical mixing. We're melting and stirring them together. We're not chemically reacting. An alloy is literally just stirred together, and yet we still get new properties from them being mixed together. Okay?
Remarkable strength come from. In metals like iron, the atoms are packed together like sheets of marbles. But when pushed or pulled, they can slip and slide past each other. But steel also contains carbon. The carbon atoms fit in between the iron atoms, limiting their freedom of movement and making it harder to pull them apart. Steelmakers long ago learned that by adding more carbon, you can increase the steel's tensile strength, but you give up flexibility, which is something that the arresting cable needs to wind and unwind. The trick is to find just the right balance.
So steel, very popular common alloy, is iron melted and stirred in with copper. And they've known about this for a very long time. And so they're like, oh, if a little carbon, I don't know why I said copper, sorry, carbon. They were like, if a little carbon's good, isn't a lot of carbon better? Well, not necessarily. It depends on the properties you want. The more carbon you add, the more extreme the tensile strength is, but also the durability, the elasticity, not so much. So yeah, it's great that you'd have a very strong sword, but if after the 4th time you whack someone with it, it breaks into pieces, what good is that? So the alloys give us new properties, and we constantly try to find new alloys by figuring out different mixes and even just different percentages with the same ingredients. Now, all that said, there's only two types of alloys. So you need to know these two types of alloys. Be sure you put these down, okay? There's substitutional alloys. Write this down. Substitutional alloys is where atoms of similar size replaces each other. Sounds like a substitution to me, you know? You got a football player who gets injured. You don't say, oh, we lost a lineman, let's send in a kicker. No, you substitute a lineman for a lineman, right? Yeah, of course, okay. So if the atoms are similar in size, then they will be substitutional. Interstitial, inter means between, interstitial, and be sure you're writing this down, is where one atom is big and the other atom is little. And so what the little atom gets to do is like work its way in between the big atoms. See how these little tiny, this would be steel here, little tiny carbon atoms stuck between the iron, keeping them from moving as much, okay? Up here, this might be like bronze, where I have copper and tin, which are roughly about the same size, and we stir it up. But copper turns green, and the little bit of tin actually keeps it a nice brown color and prevents it from weathering. So we get new great characteristics just by stirring them up, okay? And it's possible if 3 elements or more in the mix, that it's a combination of both. So again, you want to look at the size of the atoms. If they're similar, substitutional. If they're different, interstitial. If one is similar to the other, but then a third one is smaller, you could have a mixture of both, interstitial and substitutional. Okay. If you've got 3 and they're all similar in size, it's all substitutional. If you've got 3 and 2 are small and 1 is big, you got 2 interstitials with that one. So it really depends on the situation, but there's 2 classifications, and it could be a mixture of both. Okay, that was our special topics. That's what we need to know for there. You're actually going to practice that a bit in Canvas. Okay, so that finishes off our third and final set of notes, metallic bonding. Be sure that you keep these notes safe because you're going to want to be using them on our practice, and I will see you sometime later.